broaden his research exposure and international experience, Professor Awasthi pursued a postdoctoral fellowship at the University of Applied Sciences, Upper Austria in Hessenberg. During his postdoctoral tenure, he engaged in collaborative research, further honing his expertise in numerical analysis of differential equations and computational methods. In 2010, Professor Awasthi joined the Department of Mathematics at NIT Calicut, where he currently serves as an associate professor. Over there, he has established himself as a key faculty member, actively contributing in both teaching and research. Professor Awasthi has made significant contribution to academic mentorship. He has guided 6 PhD scholars to successful completion and supervised more than 20 master's students, fostering a vibrant research culture among his students. In addition to his research and teaching, Professor Awasthi holds important administrative responsibilities. He is currently the chairperson for the Center of Indian Knowledge System at NIT Calicut. Professor Awasthi is an active member of several professional bodies, including the Society for Industrial and Applied Mathematics, SIAM, American Mathematical Society. His association with these organizations underscores his engagement with the global mathematical community and his dedication to staying abreast of the latest development in his field. Apart from that, Professor Awasthi has published numerous research articles in International Journal of Repute like Applied Mathematics and Computation, Numerical Methods for Partial Differential Equations, Journal of Computational and Applied Mathematics, and many more. Over to you, Professor Ashish Awasthi. Over to you, sir.
Yeah. Thank you, Dr. Vikas, for a nice introduction. So first of all, I would like to thank to organizers, Dr. Vikas, Dr. Singhal, for giving me an opportunity to speak and discuss with young colleagues, young friends, and some of our teachers. So today, I would like to talk about, as per the assignment given by Dr. Singhal and Dr. Vikas, that I'll talk about the Matlab programs for some of the numerical methods. And these methods, basically, which are given to me, are the root finding techniques. One thing, another one is the interpolation and extrapolation and numerical integrations, and something about the matrices, how to write the matrices in the Matlab. First of all, from audience side, I would like to know whether I'm audible to everybody. Can you write in the chat box?
Yes, Professor Awasthi, you are audible.
Okay, thank you, Dr. Singhal.
Yes.
So let me share this my slide. I can share it, right? Just a minute. Is there any option to share the window? Actually, one of my PPT is open, so I have to go to file and open it. Can you guide me? Is this PPT is visible to all of you?
Yes, Professor Awasthi.
Okay. Thank you. So once again, thank you, Dr. Vikas and Dr. Singhal, for giving me this platform to speak over my experience on numerical analysis, especially root finding techniques, interpolations, and integrations. So good morning, one and all. Let me see. This is moving now. The slide is not moving. How to move the slide actually when I'm moving slide?
Yeah, it's not moving, Professor Avasti.
Okay, top. Okay, fine. Thank you.
Now it's moving.
Yeah, that's fine. So in the beginning, I am going to start with the root finding method. And question comes that what is root finding? How does it important? Why do we need to learn this particular techniques? And what are the techniques available in the literature? So first of all, I would like to say that, you know, that though we will say that we are very advanced, we are in 2025, but frankly speaking, till now, we don't have any exact solver to handle a non-linear problem. For example, let me take my just a moment. Okay, so just a moment. So for example, if we have, I don't know whether I can write it or not. It's not possible, I think. Okay, for example, if we take a problem which is non-linear in nature. So if you look at that, if you have a one equation, so I think that here we cannot write it. Because this PPT, this file, whatever it is there, only we can show, right? Option is not coming. Top. Next time I'm doing it in my file, you just see that whether anything is there. Can you write? Can you see this? Whatever I wrote. No, it is not visible there. So anyway, so what I'm telling is that suppose if you have an equation like x plus 5 is equals to 8. Okay, those are attending this, please take out your pen and paper and write down that x plus 5 is equals to 8. And this is basically again a problem where you have to find out the value of x. So you can say that x is equals to 8 minus 5 is equals to 3. It is the root of this equation. Root means that a value which will satisfy the equation, right? So that is called the solution. Okay, now if you increase little bit complicacy, for example, if you take x square plus 5x plus 8 equal to 0. So we have done nothing actually, just we have introduced one more term, okay, which is x square. And when we add this particular term, you look at that, what is the level of difficulty we are adding it. So can I share my screen? I think that would be better, right? Rather than sharing this file, because nobody can see whatever I'm writing it.
Yeah,
So,
yeah, Professor Avasti, you can share your screen.
yeah, I will do that. Now, can you see the slide, which was earlier? Because now I am not able to see it.
It's not visible, Professor Vaste.
I am sharing my screen and it is showing that that the screen is shared. Now,
It's visible.
it's visible, right? Shayanti Das is writing that it is visible, right? Okay, so x plus 5 is equals to 8, which example I gave you. Now I'm just including here one more term. For example, like 8x plus 5 is equals to 8. Let us say that. I have not done anything. Just even though if you can remove this 8, just I have added this extra term, So you know that when you solve it, you are not pretty sure that whether this particular equation will have the real roots or it may have the non-real roots, that is called the complex roots. So the complication increased, right? And you know that there are methods you can find out the roots, whether it is real or whether it is complex. Now, if I will keep increasing, now one more term, if I add it, for example, x square plus x plus 5 again equal to 8. And if you just look at that, again, more complications are there. So if you keep doing it, if I will increase x power 4 or x power 5, so that you see that you at some point you don't have any method which can evaluate the value of x. Even there is no particular method which is called the exact method, which will tell you about the one value of x which will satisfy this equation, though it is just a polynomial equation, right? But if this particular equation will have some functions called the transcendental functions, right? So for example, if I will write e raised to power x plus 2 equal to 0. Now more challenges. Even though if it is a polynomial, still we feel that we may break it, we can factorize it and do something. Now here one function we brought in the picture, it is known as the transcendental function. So once the transcendental function came in the picture, you see that it is very difficult to find out the value of x which will satisfy this particular equation. And there is no method available which will tell you that exact value of x which will satisfy this equation. Okay, by hook and crook, you may get some value of x because of some trial and error method, but there is no particular algorithm which will tell that if we will write any alpha here, any beta here, or any gamma here, you may not able to find that value of x which will satisfy this equation for any value of alpha, any value of beta, and any value of gamma. Such problems, you can say that these equations are known as the transcendental equations. So how to find out the root of these equations? Though we are in 2025, right? And we don't have any exact techniques, we don't have any methodology which will tell about to find out the value of x which will satisfy this equation. You can understand that challenges. And question comes that why do we need all these things? Of course, it is needed because when you do analysis of mathematical modeling, which has an exponential growth, so exponential functions comes in the picture. If you look at the electrical circuits, okay, their exponential increment, exponential decrement, e raised to power x, e raised to power minus x functions are coming very frequently. Okay, so they are the functions which are very frequently coming in various fields of engineering and mathematics, biology, you can say computational biology. So these are the problems which we never will face. We will face it because they are the transcendental function and they are occurring regularly in all the engineering problems, because you know that sine function, cos function, e raised to power x function, logarithmic, these functions are there, which are everywhere present when we do any mathematical modeling of uh, biological system, electrical system, or mechanical system. And you all know that when we solve differential equation problems for a mechanical system, it is known as the simple harmonic motion, and the solutions comes in the form of sine and cosine, right? Or if you solve any problems, growth and decay, that problem leads the solution in terms of e raised to power minus x or e raised to power x. So it's not that these problems are coming from somewhere else. They are coming from our physical validated systems. And the challenges are there that how to find out the roots. And we don't have any mathematical method, okay, in terms of the pure mathematics, which will find out the value of x exactly. You see that. You'll forget about that transcendental functions. Even we don't have any particular algorithm which will solve the problem more than the degree 2. Degree 2, we can solve it by using the Sridharacharya method. Okay, and more than degree 2, like cubic equation or quintic equations, we are not able to solve it as it is by using any algorithms, isn't it? There are some algorithms working for particular cases, but not any algorithm which will treat x square similar way, x cube similar way, x power 4 similar way, x power 5 similar way. So there are techniques which will solve x square means quadratic equations. There are techniques, okay, in the literature which can solve only the cubic problems. Till cubic and quintic people has developed the technique, but they're very complicated technique. But they are the limited techniques. Only they will help only to solve the cubic problems or quintic problems in degree 4, isn't it? But there is no algorithm which will solve all degree problems like 5, 6, nothing like that. So there is no common algorithms exist in the literature. And of course, when we add the functions like e raised to power x, functions like the sine x, sinusoidal functions, cosine functions, exponential functions, logarithmic functions, when they comes in an expression, there are a lot of challenges involved. So people want to give an alternate way. So the alternate way is available in applied mathematics in the field of the numerical analysis. So numerical analysis, basically the word numerical analysis comes from the idea that we may not able to find the value of the root exactly, but we will find out the value of the root which is very close to the exact, isn't it? It's called the approximation. So when you have a value which is exact, when you have a value which is not exactly exact, but it is very close to the exact, so that is called the approximate value. And so there will be a difference. There will be difference, exact value, and you have approximate value. There is a difference. And the difference between these two, we can measure and we can give this as a name called the error. So error. So important thing is that, for example, if the exact root is 2, and by using some technique, you are getting the root 1.9, or using some another technique, you may get the root 2.1. Now question comes that whether it is acceptable or it is not acceptable, because you know that this particular problem has the root 2, but the technique or the methodology you are using, it is not giving 2, but it is giving 1.9, or the methodology you are using, it gives 2.1. Now question comes, which will we should adopt it, isn't it? So you can do some analysis based on the mathematical background. So find out the difference between 2 and 1.9 or 2 to 2.1 and see that what is the difference between these two, and based on your requirement, whether the difference is 0.1, whether you are able to accept that difference. If yes, take that method. If you say that I don't want that much difference, I want much more efficient, more closer to the 2, you just reject that and go for the another tactics. And This particular value, which is the difference between exact and approximate value, it is called the error. So we will do more analysis of that error. We will see that in what circumstances we will accept that particular error. Right. So based on our analysis, we will say that I'm ready to accept. For example, if you have done a transaction of rupees 101 and there is some flaw in the transaction and you got the 100, right? You may not able to accept that because 101 and 101 rupee you are losing and you are not able to accept. But if the transaction of suppose 1 lakh and again the same error comes of 1 rupee, right? That you may accept it because you may say that we have done transaction of 1 lakh, but this 1 rupee is unacceptable. So on what background you will say that this is acceptable, this is not acceptable? For example, if you measure the size of a, or you can say that measure the diameter of a wire, right? For example, if it is 2 mm, right? And by measuring instrument, you have that diameter as comes as a 2.1 mm. You may reject it because you may not accept 0.1 mm. But when you do the measurement of a cloth or your shirt or your pant or whatever it is, if it is a 2 meter and if it comes as a 2.1 meter, even 10 centimeter difference, right? Or maybe let us say that 2.01 meter, suppose 1 centimeter difference. So you will accept it because you feel that this 1 centimeter and 2 meter will not have any issue, right? Why? So on what background you can say that here you are able to accept 1 centimeter, but when you take the diameter of the wire, which has a 2 mm diameter, even you are not able to accept 2.1 mm, right? So why it is so? So question comes that on what basis sometimes you feel that it is acceptable or sometimes you feel that it is not acceptable. So here the idea of numerical analysis comes in picture. Numerical analysis is nothing but the error analysis. So we will say that we will analyze it, the error. Okay, basically this can be analyzed in a better way, like what type of the errors are there, but that is not my topic. So I'm telling that that is called the numerical analysis. We will analyze the error that suppose we have a method, how far from the exact, in what sense it could be directly difference, it could be in terms of the percentage error, that is called the relative error, and so on, isn't it? So that means that we are able to accept the things with certain arguments, and these arguments are there in a branch of mathematics. It is called the numerical analysis. It is nothing but the error analysis. Okay, fine. So now let us come back to our root finding techniques. So root finding techniques started with a very natural instinct based on the intermediate value theorem, because when you have a problem and you are willing to find a root, right, and you don't know anything about the equation, for example, you don't know where is the root, where is nothing is there. It's like that something happened and you are totally blank. So in that case, there is a tool in you can say real analysis. It is known as the intermediate value theorem. And that theorem will tell you that the location of the roots, because when you proceed for any method, you need certain information. The method will not start immediately. You should know that in what interval the root is there, right? This information should be there. So this information we can find out by using the intermediate value theorem. What is intermediate value theorem? Intermediate value theorem, it is a very powerful theorem in the continuous functions, that if you have a function which is continuous, right, in a particular domain, and right, if you look at the domain, suppose it is continuous in the interval a and b, okay, if the sign of the function at a and the sign of the function at b, okay, you can call that fa, the value of the function at a is fa, here it is fb. If fa into fb is negative, so you are particularly happy that there is at least one, because so that is called the intermediate value theorem. So the idea start from here. If you have a function in an interval a to b and you are pretty sure that this is there, then there is a guarantee of the roots. there could be one root, there could be three roots, right? Okay. But if FA and FB is positive, suppose is positive, you can say that. So in that case also there is a possibility, but there is no guarantee. There could be a root, but there could not be any root. Isn't it? So why we will go for the dicey case? We will go for the case that we will find out an interval and check whether it is continuous. Yes, go ahead, find out the value of the function which we want to find the roots. Okay, check the value of the function at the particular point A and B. Okay, if their signs are opposite, you are relaxed because there is a guarantee at least one root is there. Okay, so first of all, when you find the root finding, or when you apply the root finding techniques, before that, you should know the interval in which the root is available, isn't it? Otherwise, what happens? You all what is called that attempts will be lost, isn't it? So you have to find out at the interval. So there are actually majorly two types of the methods available in numerical analysis. One is called the method which is depending on the interval. They are called the bracketing methods. Another one is the method which work with a particular value. It is called the initial value. It is called the iterative. Both method has their own significance, isn't it? In numerical analysis, you see that some methods are very old, or you can say that they are very traditional methods. Some methods are very advanced method, but still every method had its own beauty, isn't it? So in the root finding, there are various methods. Okay, so major category is bracketing method and iterative methods. In the bracketing methods, where brackets means you have to find out the interval, methods are there. It is known as the bisection method. It is known as the regular falsing methods. Okay, while in the iterative, more popular methods are there, more basic methods are there. It is known as the Newton's method or Newton-Raphson method or second methods. Okay, these two methods are there for the iterative process. So we will start with the bracketing methods. Okay. So bracketing methods, these are the things already I have discussed about that. So bracketing method, let me go to the bracketing method here. Okay, this is the basically a bracketing method. So in this particular method, the important thing is that you have to find out the interval A and B in such a way that FA multiplied by FB should be negative. That is the most important point in this particular method. If it is not there, you cannot proceed it, isn't it? So if this particular things are there, look at that. When you start this bracketing method, it is called the bisection method. This is the important thing, because this particular things will give you the guarantee that there is a root between A and B. Okay, and now you find out that the root is in between A and B. Now your duty to make this interval shrink and give you one point, which is the value of the root, isn't it? So that is called the bisection method. How to shrink that? We cannot shrink this interval randomly. We have to follow certain pattern. We have to follow certain regulations. Okay, so what is the regulations? Here in bisection method, they said that find the simplest regulation, that find out the middle point, C. And this is nothing but basically A plus B by 2. That is the middle point. So it is something like that. You have this interval and you are sure that in this interval root is there. Which point it has the root, you don't know, you have no idea. So what we will do, we will divide this in the two parts. Okay. So now you have virtually two intervals. One is this, another is this. So whether root is in this interval or root in this. How to identify? Again, go to the intermediate value theorem, find out f of A, find out f of C. Look at that if their multiplication is less than 0, or find out the C and find out this B already there. Look at that. Okay. So if fa dot fc is negative, in that case, your root is here. The root is here. Otherwise, root in the other interval. So you see that earlier interval was your A to B. Now you shrink it to A and A to C. Okay. Suppose the earlier interval length was 10 centimeter, for example, just I'm giving you. And now that interval length is 5 centimeter. Earlier, you know that the area where or the region where the root lies is 10 centimeter, and now you are telling that the region where root lies is only 5 centimeters. So you are more happy that you have reduced by 50%, right? Now, similarly, you repeat this process. Okay, that is the beauty of the numerical analysis. They will not say that again you have to use anything else. Just repeat this process. So you find out the middle of this A and C. Again, shrink it to half of that. You say that D is nothing but A plus C by 2. Now you choose that whether root is in the interval A and D or D2. So like that, it keeps shrinking, keep shrinking till you will not reach to the root. How to identify that you have reached to the root? So root means that the value of the in this interval, which will satisfy the function f of x equal to 0. Okay, so you say that you have made a very close interval, and you find that you reach a point. For example, you reach some point E or some point F, let us say, by this process. And you say that you reach the point E where you feel that it is a root. How to check it? You put the value of E in the function F. Okay, so F of E, if it is close to 0, you can say that you have reached. For that, you have to give the tolerance, right? So these are the again problem which needs some programming skill to identify that which is the root. So you see that here flexibility is there. That's what I'm telling, that if suppose the exact root is 2 and somebody reached 1.95, right? And if he's saying that 0.05, I'm happy. Okay, done. You take this root. But somebody want that no. I want more closer roots. So you can go again and again, and you say that now you got 1.99. Take that root, isn't it? So how to do it? That means that you define your tolerance, whether you are accepting 0.05 error or you accepting that 0.01 error. That depends on you. So what happened? Actually, I'm not audible to you. Somebody is writing, use your mic, but mic is here actually inbuilt. It is there. Am I audible?
Yes, sir, you are audible.
Okay, fine. So like that, you keep shrinking it, and finally you will reach it, isn't it? How to do it mathematically, how to write the program in Matlab? So next slide is for that. Please try to understand this algorithm. Only few points are there. Find out the midpoint and then check this sign of this one. Based on the sign of this one, because you have the sign of f of A, sign of f of B, based on sign of f of C, you can find it out that in which interval root is available, isn't it? And repeat it if you want to repeat it and make the size of the interval lesser than your tolerance, whatever interval you want. There are various ways to make this closure argument. Here the closure argument is giving that the size of the interval is less than the tolerance, or you can find out that you can give another one, that the value of f of C, which comes by repeatedly shrinking it. So you can say that if it is closer to 0 or f of C is less than 10 raised to power minus 5 and so on, you can stop it. So like that you can use it, and this method is called bisection method. So look at this method. So this particular method here, if you look at this method, so you look at here that we can define this function by root is equals to bisection. I think that you are clear how to define all these things in Matlab, because it is your, I think, the third day or fourth day. So you know it that how to define this functions, isn't it? So this is a small program in Matlab which you can write for particularly for bisection method. Bisection method is not there inbuilt program in the Matlab. Matlab has very sophisticated program. It is known as the F0, isn't it? And in that, you don't have to worry, isn't it? You don't have to give interval. And so depending on the problem, MATLAB will decide that which technique they have to use. So you have a F01 function is available in MATLAB, which will use the combinations of various techniques depending on the problem. Automatically it will choose. You don't have to tell. Okay. So if you take this particular problem, x cube minus x2, I will show it actually. I have MATLAB, but I cannot show every problem. Here you look at this. This is the bisection method. So if you look at this particular program, this is the program, and in this, if you take this program and now you want to call this, you look at that here. I will go back to the slide. So look at the slide here. You have to call this. So how to call it? You have to call like this. This function has to be called on the command line bisection at the rate. Okay, this function you have to define and give the tolerance. So I will write the same thing here. So I will write here root equal to the function name, which is bisection. Okay, and at the rate x cube minus x and minus 2, right? Okay, minus 2 comma a, which interval? It is 1 and 2, and the tolerance depending on you. So suppose if I'm giving 1 e raised to power is there, 1 e minus 0.4. Okay, so this is the tolerance. So here everything is defined in one line, and see that I think something goes wrong here. Just look at the slide. Okay, forget. I forgot to write that x. Sorry. This is my syntax error. Okay, so I will repeat it. Yeah, I'm using online Matlab, so I'm very comfortable. Yep. Okay, this is the x. Okay, so this is the, actually it is working that because you have to define it, because symbolically it is taken. So it is defined it, you got this particular value of the root, and you see that this is the root between 1 and 2. Okay, so like that, you can write the function and then make the input values and you will get the roots, isn't it? Okay, so here we have made that the interval is between this. If you suppose change the tolerance, for example, if you change the tolerance, so just I will make it. Okay. Suppose if I make the tolerance here 6, that means we want the interval should go up to 0.0, the difference of the interval, okay, will go up to 0.000050 then 1, and still you see that this value is coming, isn't it? Why it is so? Because that is again here analysis comes in picture, that it will make the sequence of the solutions, and you know that an infinite sequence, if it's convergent, it will converge at 1, right? So it basically you are getting a convergent sequence, right? And that will converge to one point, and that one point is nothing but the root. So if you are learning applied mathematics, numerical analysis, you see that you are learning how to use your learnings from real analysis, linear algebra to the practical problems. Okay, so this is the case. Okay, now let us see that graphically, if you want to analyze more about this particular method, isn't it? So look at that in the interval 1 to 2, you analyze that there is a possibility of the root. Why it is so? Because they are opposite in sign. Now you make the half of the interval, okay, 1 to 2, and then you have gone from 1.2 to 2, 1.5 to 2, right? 1.5 to 2, and you found that there is a root. Shrinking it, then you have to go 1.5 to 1.75, 1.5 to 1.625. So you see that the root is shrinking, because, and 1.5 to 1.5625, and so on. Where is the root? Wherever it is cutting the x-axis. So you see that you are shrinking. Whatever the dots are there, it will tell about the interval. So your interval becoming thinner, and you will finally, because here only we have shown only few iterations, right? But you have to go for more iterations to get the value of the roots, and they are very faster. Actually, if you are using Matlab, faster in the sense that we will visualize it is fast. But if you write the program in Python, or you can write the program in C++, that may give less time actually, but the time itself is a microsecond. So we won't analyze these particular things. So this is the graphical way how this interval is shrinking. Okay, so this is about the bisection method, which is the first fundamental method of finding the root of any particular problem, especially nonlinear problem or transcendental expressions. Okay, so you can easily find out, but this method is again very traditional methods. It will take time to give you the value depending on the problems, isn't it? But it will give you the value 100%. There is no chance if there is a root, it will give you the value of that particular root, isn't it? 101%. But it may take time. It may be a it is basically a slow process. I'll tell you that which method is slow and all. Okay, now in a similar category, there is a method called the regular falsy, or a method of false position, isn't it? So I'm giving this as a homework. You can go through that regular falsy method, which is very similar like the bisection method, because in bisection method we are making that use of bisection, but it is not like that. In regular falsy method, they are using little advancement, isn't it? So just to go through that, but that is again a method basically based on the brackets. Yeah, what happened actually, Himanshi, are you not able to hear me? I got some pop-up message that my voice, please tell me that if it is the case. Okay, so now let us go to the next method. It is okay, clear. Surya Rao. Okay, fine. Thank you, Surya. Okay, now next is the basically it is known as the iterative method. Okay, this is called the iterative method. So one bracketing method we have done it. Another one is we will do the iterative method, and the iterative method, the most popular iterative method is the Newton-Raphson method. Okay, or people call it as the Newton's method, isn't it? And this method basically, if you look at the derivation of this method, it's a very intuitive, comes from the Taylor series, isn't it? So if somebody will ask you that why do we need the Taylor series, why Taylor series is taught in mathematics, so you can say that it has an enormous application in numerical analysis, and one of them is the Newton-Raphson method, isn't it? So what this method is telling, that this is the iterative formula for this particular method, isn't it? If you want, I can show it that here how this method has been come. So you have the problem like f of x equal to 0. Okay, and so you have taken a point x naught. Now you are writing the Taylor series. So you know that the Taylor series is like this. Okay, so this is actually one question was asked by some BTech student, that sir, why do we need the Taylor series? Taylor series is a powerful series. If you look at that, if you know the value of the function at one point and derivative at the same point, right, you can find out the information about this function all neighboring points. Suppose there is this is basically a point I can call this as a x0. Here you know the value of the function, you know the derivative of the function, everything you know only at one point. Okay, and with the help of that, we can find out the information of this point, find out the information of this point, find out the information of this point. In all the points, we can fetch the information just by knowing one point. It's like that, what is called that crime branch. It will take all the information just if you have the information at the one. Okay. So here, if you look at that, if h is small, we can ignore the higher terms and we can find it out from here that this affects not this particular things, right? So from here, you can say that it is fx naught plus h minus fx naught by h is your f plus h. Okay, so here, now look at this. When we write that xn plus 1, that means it is something like it is in the advanced stage. Okay, xn plus one more iteration you can give it. With that, you can find out that xn plus 1. That means you have the sequence of this function. Okay, you don't write this because if it is equidistant, it is fine, but we don't know. So this is the sequence n equal to 0 to infinity. So we are generating the solution in terms of the sequence. Okay, so here we can find out the value by using this iterative procedure. So one procedure is like this x0. So we can find out here. Look at that fx now xn plus 1 by using the information at xn. So if you know x0, you can find out x1 by using x0 minus fx0 f dash x0. And then again keep doing it. Okay, and then you will get the next one x2 by using this x1 fx1 by f dash x1. Like that, you continue it, you will get the solution. Okay, but again question comes that here what is h? You don't confuse. I have given the this by this h is here. I have taken that h is as a xn plus 1 minus xn. Okay, through that it is given. Okay, fine. So in that way, we have given this particular value. Okay, fine. Okay, so, but it may not necessary that, but for the derivation, it is used like that. Okay, so you will get the sequence of the solutions x0, x1, and so on. And finally, you will reach the destination of your roots. But there is a problem. What is the problem? It is, look at that, when you use this method, you have to pretty sure that the denominator, which is f dash xn, okay, it should not be 0. That I have not mentioned here, but it should be that this particular function should not vanish its derivative at any of the points. For example, you have, suppose you got the root in x5, right? So you will not get the 0 f dash at x0, f dash at x1, f dash at x2, and f dash at x2. That is the important. If suppose you are taking a random problem and somewhere you got that the derivative becomes 0 at the iterations at xn, then this method will give you any, and this method will not give you the solution. It will not converge because when denominator is 0 or close to 0, these particular problems will blow up and you will get the not a number. Okay, or you will get something wrong, isn't it? So this method is good, but it has a drawback that you need the derivative information. Okay, but if you are choosing x0 wisely, okay, there is a theory behind that, there is a mathematics behind that, it is called the convergence, that if you are choosing very wisely this particular value of x0, how to choose wisely means that if you are choosing the value of x0 which is close to the exact solution, okay, then this method will converge 100%. So the convergence criteria, it is showing that the value of initial gas should be sufficient close to the exact solution. But question comes that when we don't know exact solution, how can you choose it? This is the practical problem everybody is facing. When people use Newton-Raphson method and they said that Newton-Raphson method 100% give the solution, why it is not giving? sometimes when you are taking the initial guess, isn't it? Because there is no methodology to choose the initial guess. You can take any random value. So if it is close to the exact solution, it will convert it. Otherwise, sometimes it may not give you the correct answer, isn't it? So it has been suggested that you do one thing, that for few steps, go for bisection method. Suppose 4 steps you have gone for bisection method, you have interval, you have shrink the interval, and you are sure that in this particular interval there is a root. So you choose a value of x naught in that interval, any value you can choose. And with that value, if you go for Newton-Raphson, there is a high chance that you will get the accurate value, isn't it? So Newton-Raphson method is good, fast, everything is there, but it is little bit sensitive because you have to calculate the derivative. So Newton method is good, fast, everything is fancy. Only the difficulty is the derivative, isn't it? And now, if you have a long expressions, it is really challenging to find the derivative. It is not that easy to find the derivative, isn't it? So these are the challenges with the Newton method. So this iterative method is good, but there is a challenge. And how to write that? So again, you can make the routine. You see that it is very simple routine or simple function. Root, you can write it down. Newton f df. So you have to make 2 inputs, f and as well as df, and then of course initial guess, and then you can give the tolerance. Only one line formula you have to write it. You will get your root. So very simple. Okay, so if you use this particular example which we have done earlier, so x cube minus x minus 2, but you have to find out this derivative in advance, isn't it? But here we can find out, but in some cases it is really challenging to find out the value of the root. So it will give you the same value. Okay, it is not like that. Okay, now next. Another iterative method which just I want to tell you. Okay, these are the actually graphical representation of the Newton's method, how the roots is basically approximate because it's involved the derivative, it is the slope of the tangent. So basically it is called also known as the tangent method, isn't it? So you are just finding the tangent at one particular point, wherever tangent cuts to the x-axis, that is the root. Take another tangent from there, okay, and again it will cut. So through that only we are finding the roots. It is known as the tangent method. So these are the graphical ways to identify that how the tangent is moving towards the. So you see that when tangent cut the x-axis and the function cut the x-axis, if these two are matches, that is the root. That is the graphical concept of the Newton method. Okay, another method is called the secant method. So what is the secant method? Secant method is nothing but basically you can say that it is the advancement of the Newton-Raphson method. In the Newton-Raphson method, you saw that there is a problem. Screen is not visible. I don't know, but here it is visible. So when we do the secant method, the drawback of the Newton method is the derivative, which is troubling us, isn't it? Because every time you have to calculate the derivative. So they have given the idea taken from the numerical derivative. Again, the Taylor series, you can say that you can write f dash x, which we have written f x naught plus h minus fx by divided by h. So through that, the term which is extra given in terms of the derivative, this part. So this is nothing but the numerical derivative. So they have used the numerical derivative. They said that this is something like that, you know, that when you go to a restaurant and you see that varieties of the paneers they are serving, right? But if you look at the ingredient, there is a very slight difference, isn't it? Same thing. The secant method and Newton's method only user friendly is the secant method. You don't have to find the derivative, but rest of the property will be followed from the Newton-Raphson method. So this method is good because you don't have to do the differentiation, isn't it? So it is a derivative for you. But this is similar like that only. Okay, so you can highlight that secant method does not need any derivative information. So it is more user friendly compared to the Newton-Raphson method, but nothing comes free. So secant method, you need the 2 initial approximations. In the Newton's method, you need 1 initial approximation. Here you need the 2 initial approximations. So you see that bisectional method, little modification if you do it, okay, in terms of the graph, you will get the regular fallacy. Now, Newton raption, if you do little modified in terms of the derivative by using the numerical derivative technique for the Taylor series, you will get the second method. So, second method, Newton raption, are closed, both are iterative, while a regular fallacy and bisection, they are somewhat closer. Okay. So this is the code. Code again, it's simpler because this is coming from the Newton. In the Newton, just modify, remove that f dash x naught, put that value here. Look at this particular value, whatever we have given. Okay, from the formula, you will get it, and the same root you are getting by Newton. But only thing is that you have to take the two initial approximations. Earlier, we have taken only one initial approximation. Now we need to take the two initial approximations. So this is the second method. So learn the method. So please note that Matlab code or Matlab program, you don't have to write whatever it is here, whatever I try to write, but no like that, nothing like that. Try to understand the algorithm, write the code of your own way, isn't it? If there are 80 people attending this particular class, then you are, if you're writing your own, then 40 to 50 variety of the codes will come, because nobody will follow whatever it is written, isn't it? You know the syntax, you know the concept, you write in your ways. Okay, now next is this is the actually method which is inbuilt in the Matlab. This is called F0. That means finding the zeros, root means zeros of the function f. This is inbuilt in the Matlab, and this is actually kind of a smart method, and this will take things its own way, isn't it? Okay, so the program is written in such a way that depending on the problem, depending on the initial value, or depending on the brackets, if you don't give anything, then it will analyze the problem, find out that whether bracketing method is superior in this particular case, or iterative method is superior in this particular case. Automatically it will choose and give you the results. So F0 is an inbuilt method. They are using all the methods which are there in the numerical methods. It is their background codes are there in Matlab, but if you use it in the command window, you don't have to do anything. Just call this function F0. You don't have to define this function. It is inbuilt function in the Matlab. Just you have to give the function, okay, and give the initial guess if you have available initial guess. Okay, if you have available with the brackets, you go with the brackets. That's up to you. Okay, if nothing is there, it may also work. It may take its own default one. So in that way, you can find out the solution of the same problem. I'm taking the same problem from the beginning: bisection, Newton raption, second method, F0, and F0 is inbuilt in Matlab. Suppose you are finding a root of a problem and you are not aware of anything, use F0s, get the value of this, isn't it, without knowing the algorithm. Okay. And the benefit of this that does not require any derivative. Okay, convergence is guaranteed again because it's an adaptive method. It will take its own way. Okay, so if you look at that overview of all the methods which we have discussed, bisection, Newton raption, second, and F0. So here it is written: bisection is a slow, derivative information is not required, reliability is very high in the sense that there is a 100% guarantee that you will get the solution. Okay, Newton raption, speed is fast, of course. The derivative required, yes. Reliability is good depending on the initial guess. I forgot to write it that it is reliability is good, but the reliability is also not 100% good because it will depend on the initial guess. If your initial guess is not robust, isn't it, then sometimes you will not get any root by using Newton raption. Second method is better than the Newton raption method. Again, reliability is a question mark here also. It is good if it is initial guess is close to the exact solution. But plus point is that you don't have to find explicitly the derivative. Okay, the method itself will take care of everything. Now F0, because this is a combination of bracketing method, iterative methods, isn't it? Okay. So here derivative is not required, nothing is required here, and they will choose because they will take the benefit of bisection, they will take the benefit of the Newton raption, all combinations, they will give you the results. So this last one is not the basically algorithm based method, it's in the hybrid methods. The algorithm is given by the Matlab themselves. They may design this method in such a way that it will give you the best solution, isn't it? So these are the ways you can find out this. But if you are not using Matlab, then bisection you can use it. You cannot use F-zeros in any other platform other than the Matlab. But bisections don't need any. There is no copyright for bisection. There is no copyright for the Newton raption or second method, but there is a copyright for the F-zeros. We don't know what is inside. Okay, fine. So these are the comparison of all these particular methods. If you have any questions on these methods, and please note that till now we have open problem that if you look at that numerical value of the convergence, bisection is called the convergence of order 1, Newton raption is called the convergence of order 2, similar second is also near to convergence, not exactly the 2, it is less than 2, and F0 depends that what exactly they are choosing it, isn't it? So bisection method is very slow in terms of the convergence, Newton raption is very high, but again it's a high speed train, the risk is more. Second also same thing. F0 is a different. Okay, so they are not concentrating in the convergence. They depend that sometimes they may use the hybrid one. So we can't say anything about the convergence. Okay, so these are the things which I taught you till now. So if you have any question, you can ask. Any questions? So can we take 5 minutes break? Because 1 hour is over. Yes.
Okay, Professor Basti. Uh, Students, any question? If you have any question, please write in the chat box. Any question from participant side? Okay, now it's a time for a 5-minute break. So after 5 minutes,
Yeah, after 5 minutes, I will be
we'll
here.
join back.
Okay, I'm audible now.
Yes, yes, sir, you are audible.
Fine. So, mhm, fine. So now we will be here, and now we will go for the next topic that is known as the interpolation. So before that, can you write it that what do you understand about the word interpolation? Anybody? Just on the chat box, you write that what do you understand about the word interpolation? What is interpolation? You can write in chat. At least you write that earlier you have heard the word interpolation. Anybody from the audience?
Yes, sir, it has been discussed.
Okay, fine. Already here in this. So interpolation basically is just something like that. Look at this. Suppose you have a lot of so it is something like that. You have lot of data points, right? And now these data points are known. Here you know, suppose x axis, y axis, and these are the coordinates of these points, which has the combination of x and y. So call x naught, y naught, x1, y1, and so on. So you can call this as, suppose, x5, y5, isn't it? So if you have a trend of something, for example, the gold price today, tomorrow, right? Or maybe today, tomorrow is more easy actually. Suppose you have the gold price of every Monday or every Tuesday, right? So you have two things, that the day information you have it and the price information you have it. Suppose you have the information of the gold price on Monday, every week Monday. Now you want to know that what is the gold price of particular day, which is not the Monday. Then Monday you already know it. And suppose you want to know that in the month of June, in the first Tuesday, okay, of the week, June month week, first Tuesday, what is the gold price? So what happened actually by this? It may not be correct, but you some information which you want to fetch, which is not there in these points, but in between these points, like this. If you want to find out that, isn't it? Isn't it? So that particular process is known as the interpolation. So you have the nodes, we call it the nodes. So nodal values, you know it, but intermediate value you want to identify. Okay, so that particular process, how to identify that particular process is known as the interpolation. So the best way of finding the interpolation is first you look at these points, isn't it? Make a curve which will pass through all the points. Okay, there could be various curves, depends that what type of the interpolation things you are using it. So you pass through all the points, that means it is interpolating 100% on the given data points, isn't it? And then that particular curve, if it is a polynomial, we call it as a interpolating polynomial, isn't it? So there is a process how to find that interpolating polynomial. Okay, so we will discuss that. So now look at that. Suppose here it is there, estimating values between known data points. So this is about the interpolation. It is used in various places like statistics, engineering, numerical analysis. So if there is a two data points, look at the figure A. You can easily fit by using the line. If you have three data points, you can make use of a curve which will pass through these three data points. You can call this as a parabola or quadratic curves. If you have a four data points, you can fit another curve, okay, which will pass through. This is basically a cubic curve. Okay, there are four data points, isn't it? So that means if you find a curve which will pass through all the data points, not only few data points, isn't it? All the data points, we call that as a interpolating polynomial or interpolating curve. But with the help of that curve, if you are identifying the value between the data points, that process is known as the interpolation. Interpolation is nothing but it is something like that you are making use of the data points, fitting a curve, okay, and with the help of that curve, you are identifying the missing points or the values of the points which are in between the given data points. So basically, if you look at the simplest interpolation, it is known as the linear interpolation. That means interpolation where data points only given in the two forms. 2 points are there, and these 2 points you can always use, even though without any formula, you can use the equation of the line. So if you have a 2 points, you can always write the equation, which is nothing but the straight line, because that formula, if you remember it, that x minus x1 is equals to y2 minus y1, sorry, x2 minus x1 divided by y1 minus y2, and so on. Okay? So based on that, you can define it. Okay. So here, look at this first one. That's what here written, that if you have 2 data points, x0 comma y0, and another one is the x1 comma y1. So you can write that y minus y0 is equals to x minus x0, and this is the slope. This is the slope of the line, isn't it? So you can easily write it down. Now suppose if you have n data points, so you know that this is basically a polynomial. If you have n data points, okay, or n plus 1 data points, so you can fit a polynomial of degree n. Okay, so if a polynomial of degree n, it has a n plus 1 unknowns. Look at this, a0, a1, a2, an. And if you have the data points is n plus 1 numbers, isn't it? So each data point it has to pass through. So there is a n plus 1 unknown, there is a n plus 1 equations, isn't it? And you can precise get the curve. So what I'm telling is that if you have n data points, let us say xi comma yi, okay, and here I is 1 to n, and then you can say that by this yi is equals to a0 plus a1 xi plus a2 xi square plus dot a and xi. So there is a I is 1 to n, n plus 1, sorry, n plus 1. So you have n plus 1 equations, and you have a n plus 1 unknowns. Okay, you can find the unique values of a0, a1, and an, that n plus 1 unknowns. Okay, and then we will get the polynomial, and this particular polynomial, it is known as the interpolating polynomial. But this is the theoretical aspects, which is tedious work. Suppose if it is a 1 data points, you can get a line. It is a simple by using the equation of the line. If it is a 2 data points, still it is okay, because only 3 unknowns are there, 3 equations are there, you can find it out. But if it is more data points, it is really challenging to identify the interpolating curve or interpolating polynomial, which will pass through all the points, isn't it? Because n plus 1 equations and n plus 1 unknown, then again it becomes a challenging problem. So there are methods given by, again, long back by Newton's and Lagrange. So they have given a technique to identify the interpolating polynomial without solving the system of equations. And the corresponding polynomials are known as the Newton's interpolating polynomial or Lagrange interpolating polynomials. Okay, and both interpolating polynomials functions are available in Matlab. That is the practical things, isn't it? So you don't have to write your own program if you are using the Matlab platform, but if you are using any other platform like C++, you have to learn the algorithm and make use of the algorithm to write the code. So again, I will repeat it that the information which is there in two data points, and you want to fetch anything in between the given data points, okay, that particular process comes from the interpolation. Again, you have to find out a curve which will pass through all the data points. So the curve is connecting from one point to second point to third point. In between, you can find out the value because you have the value of the curve, or you know the curve equation. So now Newton's interpolating polynomial based on the idea of Newton divided difference, isn't it? So he has used the term divided difference, and through the divided difference, the term has come. You might have seen the finite difference, isn't it? When the divided difference has the equal intervals, isn't it? That means the length of the interval is same all the time. Then the divided difference becomes the basically finite difference, isn't it? So Newton divided difference is most popular interpolating polynomial because crystal clear algorithm is there, and the plus point with this algorithm is there that when you have a data points, two type of the data points are available. One is called equidistance data point, another is unequally spaced data point. So equidistance or unequally spaced. That means the distance between two data points is same. So for example, if there is a data point 1, another one is 1.5, then 2, 2.5. So everywhere equal distance is there, 0.5, 0.5, 0.5 in the x direction. Okay. If you have a randomly scattered data points, then you don't have any other option. You have to use the Newton divided difference or Lagrange interpolating polynomial. But if it is equidistance, divided difference becomes much more simpler because it will convert it to the finite difference. Okay. So now see that how this is working. So as we have already seen that the if you have two data points, you can always fit a straight line, and the same thing is given in the basically divided difference. So look at that. If you have a divided difference, and you will get the interpolating polynomial. Here we have written px. So we have not used the f because just we have used the f for the data points. So this can be written as by using the Newton interpolating general polynomial. You can write this is called the Newton's first divided difference. This is known as the Newton's second divided difference, isn't it? Okay, this is nothing but the slope. So basically, again, it is similar like the slope of the line, isn't it? So this is the linear form of Newton's interpolating polynomial if you have a two data point. Look at the two data point is there, x0 and x1. So x0 corresponding to fx0 and x1 is corresponding to fx1. Now, if you have a three data points, for example, if you have a data point x0, x1, x2, and corresponding f values are available, then you can fit the quadratic polynomial, you know it, isn't it? But in Newton divided difference, you have a pattern. You see that first we will use the first and divided difference formula like form, then second divided difference form, and then third divided difference form. So it is very convenient because it has a pattern. So you can use, suppose if you have a 4 data points, just extend the same pattern. If you have 5 data points, you can extend the same pattern, isn't it? So learning is easy if the learning follows through a pattern, right? So that is the beautiful thing with the Newton's divided difference. It has a pattern and it is really simple to work with. So this is the Newton's divided difference. So here the value of this divided difference is given. First divided difference is nothing but the function value. This is called the first order divided difference, which has the value as the slope. This is the second divided difference. Look at this. All these things are given. You can note it down also if you wish to. Now, if you want to write the Matlab code for this, isn't it? So suppose data points are here. What are the data points? 1, 2. Here I have given x different, y different. Y means f at x. Okay. So 1, 2 is the first point. Second is the 2, 3. Third one is the 3, 5. So like 3 data points are there, and you know that you can fit always the polynomial, right? So through that, you can find out the Newton's polynomial by using the Newton's divided difference. So you can see that this type of the code, you can, if you want, you can make use of this, and get the value of, if you see that there's a 1, 2, 3. If you want to value at 1.5, you will get it. If you want to value at 2.5, you will get it. So anything in between the data point, if you want to find, you can find out, and that process is known as the entry. So here we have defined that this first difference 0 and 1 by this formula, which is there in the previous slides. F12 again, then this is the second divided difference we have calculated in a similar way. Okay. And then through this particular routine, we can, this is there, and we can use this particular routine. It is available in the Matlab. Just you have to give the inputs about the divide difference and the data points. You will get the value. You will get the basically polynomial. And if you want to find the value at the point between the data point, in between the data point, that is called the interpolation, you can easily find out just by giving the value here, x value. So x values here, they have given 2.5, you will get it. Okay. So this particular routine is available. Only inputs are required, data points and the divide difference. Yeah. So explanation, you can see that input data points, okay, compute the first order divided difference. Of course, through that you can find out the second order divided difference. Then you can use the polynomial by using the Newton's interpolating formula and evaluate at any particular point. You look at that here, it is written actually. Okay. This is the routine, Newton's polynomial. Here, this formula comes from here. You can use this formula to write this. You can easily evaluate and you will get the value of the function at any point in between. Here it is done for the 2.5. Okay, this is the basically generalized Matlab code. Okay, you can make use of this. So you can write the generalized Matlab code for the Newton's interpolating polynomials. Okay, by using the formula, you write it down. Now you can give any data point, it will give you. So any one of them, you can make use of that. I think it is there in the Matlab also, Newton's interpolating polynomial. But here, this idea is given in the code forms. Okay, you can write it down by using the algorithm. But if you go to the another interpolating polynomial, which is again similar like the Newton's divided difference. Okay, it is known as the Lagrange interpolating polynomial, and which is again particularly very efficient for the unequally spaced data point. So this is the formula. Directly I have written, basically you have to calculate here again the Lagrange polynomials, and through Lagrange polynomial you make sum of the all Lagrange polynomial, you will get the Lagrange interpolating polynomial. But calculating each Lagrange polynomial, it is a little challenge in itself, isn't it? So this particular process is really good, because Lagrange polynomial, which comes through the data points, is really more efficient, more accurate, okay, compared to the divided difference. But again, it is very efficient only if you have less data points. Suppose you have 1,000 of data points and you want to find out, it is going to be a challenging task by using the Lagrange, because the complications are there in finding the Lagrange interpolating polynomials, because product is used. So this is the formula, Lagrange interpolating polynomial, and this will lead some oscillations for large data sets, and this is known as the Runge's phenomenon. Actually, if you take the more data points, for the small data points, it's really good. And what is the plus point with this? Actually, this routine is available in the Matlab. It's like that you have seen in the previous also, that F0 is available in the Matlab. While this particular routine is available in the, you don't have to calculate the Lagrange interpolating polynomial in Matlab. You can just use the inbuilt function called the polyfit, isn't it? It will give you the value of interpolation, value of the interpolating polynomial. It will, if you want to write the interpolating polynomial, okay, because it is a symbolic computation, it will not give. But if you want to find the value at a particular point, it will give. Okay. So you can identify this particular routine or function in the Matlab. It is called the polyfit. Okay, it's a polynomial interpolating. This is default one. Okay, so here it is a quadratic fit because it is written x comma y comma 2. 3 points are there, so 2. Okay, you will get it. Okay, and then find out the value of the interpolating value of the point 2.5. So you will get that poly value. Okay, 2.5. This value you have to give it. So it will tell you about the interpolating value at 2.5 at x equal to 2.5. Okay. So Lagrange is really good. Okay, that is the first fundamental interpolating polynomial. Study from the numerical analysis, they will start first Lagrange interpolating polynomial, and even though Lagrange interpolating polynomial can lead to the divide difference polynomial, but learning divide difference polynomial, because it follows a simple pattern, is easier. So that is why we have started with the Newton's divided difference interpolating polynomial. Okay, and you can use the Lagrange interpolating polynomial here, because the idea here to learn for the Matlab just use the polyfit, will help you to find out the interpolating polynomial. Now, so these are the interpolation, and now if it is suppose you have a data point which is equally spaced data points, these are the equally spaced data points which we have taken into consideration. But then you can use the finite difference. Actually, finite difference already you are doing a lot of your courses, and you have seen that finite difference means that it is applicable only on equally spaced data points. That means the distance between two data points, x data point, not the y data points. X data points is the same, right? So x1 minus x0 is same as x2 minus x1. In that case, you can use a finite difference. A Newton divide difference leads to the finite difference. So in that way, you can use the interpolation. And these are the interpolation actually, again, in the modern life, people are not using this interpolation. Why it is so? Because there are again more advanced interpolations are coming like interpolating polynomial. They are very, very crude interpolating polynomials, in the sense that it has been analyzed that if you have 4 data points, if you are using the cubic curve of, you have 5 data point, you are using a curve of degree 4. But practically, if you have a curve of degree 4, isn't it, which is really a complicated structure. You look at the, and when these points passes through the curve, we are not pretty sure that it's basically there is a joint. When there is a curve between 1 to 2, second data point to third data point, 4 data point, we are giving polynomial. But actual these data points may not come from these curve data points. We are forcefully doing it, isn't it? So sometimes the in-between value which comes from this interpolation is not very accurate. The idea is that the data points come from some experiment or somewhere, they may not follow any pattern, isn't it? So the idea later on evolved that we can go more advanced interpolating polynomials. One of them is the Hermite interpolating polynomials. That means that is interpolating not only the data points, it is also interpolating at the derivative at the data points. Data points are there, x0, y0, and all. Then it is not only these are interpolating, but also that x0 at derivative at that particular x0 also will be interpolated. It is known as the Hermite interpolation, which is much better than the normal but again, Hermite interpolating polynomial becomes challenging, isn't it? Then people have said that it is not advisable to go for a big polynomial. It is always advisable to go for a small polynomial. Then the idea of piecewise interpolating polynomial has come in pictures. And the most popular piecewise interpolating polynomial there in the literature, it is known as the spline interpolating. Splines, isn't it? And spline is something like that. It will interpolate data points, its derivative, not only one derivative that depends on the spline which you are using. It will interpolate the first order derivative, second order derivative, and so on. Isn't it? So the cubic spline is very popular because it interpolates data points, function. That means at the joint where these curves are matching, they will take care of the first derivative. First derivative means that slope, isn't it? It will take care of the second derivative. What is the second derivative? Means it is a curvature, like it is a convex up, convex down, everything will be taken care. So these type of the interpolating polynomials are most popular. Cubic spline. Dr. Vikas has done a lot of work in the splines and knows better than anybody else. So interpolating polynomials. Okay. But time is limited, just I am giving it in a very brief. Okay, in Matlab, some routines are available if you look at that. Okay, otherwise there is an interface, you can define it. Okay, many routines, many functions are available in still in the Fortran or C forms. It is there in the free of cost. But you should know that these routines also can be integrated, can be used the interface and integrated with the Matlab. So if you are running Matlab code, if you need some particular routine from the Fortran or from the C, there is a command, there is an interface, you have to define it. It will go there, take the values from there, run it here, isn't it? Okay, so if you are give little bit more time about the Matlab is doing wonderful job for the testing the problems. Of course, for a big system, Matlab will be difficult. It may take time. Okay. Now, next topic is the extrapolation. What is extrapolation? Interpolation means that the points which you are doing in between the data points. Extrapolation is something different. It is something like that you are going beyond the limits, actually, isn't it? And which is actually know that it is always dangerous to use it. So it is something like that. You have these data points. So you fit the curve like this or whatever it is. If you are finding the values here, 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 or here, it is called the interpolation. Now, these are the endpoints. These are the dead points, right? Now you want to find something here or something here like that, which is not available in the domain actually. It's out of the domain, isn't it? So you have to bring this curve here, the value virtually curve, you bring it here and find out this value. Virtually you bring the curve here. That is called the extrapolation. Okay, so interpolation is really accurate because it is something like that is a past. If you look at that, you look at the numerical analysis, mostly we are using the information from the history. You go to doctor also, they will ask the history, isn't it? But extrapolation is something that using the history, you are not predicting about the history or predicting about the future, isn't it? So which is really challenging. So that you have to find out the value at a point, at a node point, which is outside the given data points. So nowhere inside the data points, isn't it? So that is called the extrapolation. So it is written that the estimating values outside the range of the known data points. Of course, when you go beyond that, it's kind of a future predictions. It's risky. Okay, so very highly it is written here that I have written it actually is highly uncertain compared to the interpolation. It may give you the correct value, it may not give you the correct value, like the weather predictions actually. So predictions can become inaccurately quickly as distance from the known points increases. That means nearby we can at least predict it. If it goes beyond that, it may not be accurate at all. Okay. So guidelines for the safe extrapolation. Limit the range of extrapolation. That means try to predict nearby. Use that nearby value. Again, go to the nearby value. Suppose you want to find something here. So it is suggested go something here. Then with the help of these two or previous points, you find out something here, then find out something here. Like that, you go and find out here. Don't go directly from this point to this point. It is a highly uncertainty, right? So there is a risk. And then verify results using domain specific knowledge or alternative methods. You have to cross check everything and see whether you are moving in a correct direction or not. So extrapolation, personally, I feel that know it, use it very carefully. But in the Matlab, I think it is there. Okay. So Matlab code, you can identify the routine for the extrapolation. How they are doing, I don't know actually. What techniques they are using it. So you can use these routines and you can work with it and get the extrapolation. I don't have any idea that because I have never used the extrapolation from this way. I have used the extrapolation. Me and Vikas have used the extrapolation in a different way, not like this. So I'm not pretty sure about the extrapolation, but there is a possibility, there is a function in the MATLAB. Okay, you can find out the extrapolation by using MATLAB inbuilt function. Okay. And again, you see that again, I wrote the note here. Always validate extrapolation results with caution. Extrapolation can easily lead to incorrect conclusions. Okay, it's a hypothetical thing sometimes. It's kind of a gossip actually when we talk about too many things. So we have to be a little careful. Interpolation, you don't have to worry. Well-defined techniques are available. Okay, and the next part, which is there actually, I'm not sure whether you are aware about that. How to write a matrix in MATLAB. Actually, if you look at that, the MATLAB is an abbreviation, comes from the matrix laboratory, isn't it? So the idea comes from somewhere to someone's mind that everything which we write is nothing but the matrix. And you write a number 1, it can be treated as a matrix. You write any vector, okay, it can be treated as a matrix. If you write, of course, matrix itself is a matrix, it's a two-dimensional array. And now talk about the physically. If you have a scalar quantity, that also a matrix, it's a number. If you have a vector quantity, you have already row vector, column vector, you can represent so that. If you have a matrix, again, if you have a matrix in this two-dimensional array, that also a physical quantity, it is known as the tensor. Isn't it? So if your tensor is a very interesting thing, it is very useful concept actually in the modern science, and that is well defined in the basically our MATLAB. Now they are telling about the tensor product somewhere. So very easily we can incorporate all those quantities which has a lot of physical meanings. Okay. So now let us come that how we can write a matrix in a MATLAB, isn't it? So first of all, you understand that what exactly is the matrix. So matrix basically it is an array of numbers arranged in row and columns. It follow certain patterns. You know that matrix is something like that. That has two things. One is the numerical value for, and another is the place value. Isn't it? So it's a because it is a combination of the vectors actually, right? If you look at the physically, what does it represent? It represents a transformation. It represents a tensor. Okay, so here two things are important: one physical value and the means numerical value and the place value, isn't it? So matrix is something kind of a structure where two things are important: numerical value and its place value. And now, if you want to write here, I will explain. Suppose let me see what other things are there. Accordingly, I will go. Yeah, so you can create the matrix in MATLAB is very easy. Suppose you want in the form of a row, right? So you can write, suppose this is a row vector. Let us write row vector, right? Defining now, you can use that bracket 1, comma 2, or you can space whatever you want. You can use it. 3. Okay, you just press it. It will give you 1, 2, 3. It is coming in the row forms, isn't it? So it is called the row vector. So every element is distinguished by the comma. If you write comma, if you don't write comma, here what is happening actually? If you don't write comma, then what is going to happen here? Suppose if I will remove comma. Suppose if I write 1, 2. then you see that what it will come. It will come 12. So it will not identify that you are giving the place value. It will take as a numerical value. Isn't it? Okay. Now, so if it is the case, now next is the column vector. So now we will write here column vector. The column vector is something like that. Column vector means that it has a different rows, but the element in each row it is one, right? So here you can write again. So you want to specify the rows, so you have to use the semicolon, and then just to enter it, you will get 1, 2, 3. Again, you have to tell the semicolon. If you're not telling the semicolon, it will go. If you have a space, suppose if I'm writing like this, if I'm writing like this, suppose column vector, if I'm writing like this, 1 and space 2 and then semicolon 3. See that how does it go? Will not, because why it is not coming? Anybody can tell you that it is not the column vector, right? It is not properly defined. So here, if you want to write this, you have to make use of this. Now you see what is coming. So column vector means that it has one vertical column. Row vector means that it has a one horizontal array. So they are called. Now matrix, if you want, because it is a combination of row vector and column vector, so you can write a. Suppose you want to write any matrix in the form of 1, 2, 3. Then that means these are the elements in the first row. Now you want to write the element in the second row. Now I'm writing 4, 5, 6. Another the element in the next row. Then 7, 8, 9. Enter it. You will get it. Isn't it? And lot of things you can play here in this particular platform, especially in connection with the matter. A lot of inbuilt routines are there. If you want identity matrix, for example, right? So identity matrix of order 3. Let us see what we call test. If you want all elements of order 3 by 3 matrix, which are elements are 1, 1. You want all zeros here. If you want zeros, so all these things you can practice. You just sit with Matlab. I think you can be better than me. I'm not very expert nowadays. When now, if you want to generate any suppose you want to just test something and you want to generate any random matrix. It's a random matrix. If you want to generate magic matrix, something like that, you can generate. Okay, so many routines are there, many commands are there. You can go to the help and do yourself. So matrix, personally, I feel that you can just, if you sit on computer, use this Matlab things, you can easily work with that. And these are the basic operations. Suppose you have 2 matrices, you can use in the Matlab A for the addition A plus B, so on. Multiplication, just put the star between 2 matrices, it will multiply, but the rules should be followed. You know that when 2 matrices are multiplied, that means first matrices number of columns should match the second matrices number of rows. Whatever there in the theory, that should be followed. Otherwise, you have to go for the transpose of the matrix. You just put the dash, you will get the transpose. Inverse of the matrix, that is the biggest thing. The biggest difficulty, that finding the inverse is there. A lot of algorithms are there, but in Matlab, just you write INV in bracket the matrix, you will get the inverse. Determinant of the matrix, you just write DET bracket the matrix, you will get this. Eigenvalues, isn't it? Suppose 3 by 3, you can find out. If you have a 4 by 4, 5 by 5 matrix, you see that you can easily find out the eigenvalue by using this command EIG. So if you look at here, if I'm just making a random matrix, so let us write that a random matrix of order 4. So just it is a random matrix. So 4 by 4, it is difficult to find the eigenvalue, isn't it? So let me make this. I want to find the eigenvalue of this B. So just write here eigenvalue of this B. We will go to complex, whatever it is there, it is you are getting the eigenvalue, isn't it? But if you do by any other platform, it will take more time. So in this, if the operations you are doing in connection with the matrix, Matlab is the beautiful tools. You can make use of it. And just to setting is required. And now system of equations, right? You can use system of equations by using this. Suppose you want to solve AX equal to B. Lot of algorithms are there in numerical analysis. Again, in Matlab, there is a command A backslash B, but provided the solution is there, isn't it? So please note that Matlab will give you the accurate solution if the theoretically things are fine. For example, if this case that if A is not invertible, for example, isn't it? This A inverse is not there, we may not get the unique solution. Then there will be a confusion, right? If it has multiple solutions or it has no solution, those things will be difficult for the Matlab to tell up. Okay. So theoretically, you should be fine that this has a solution, okay, unique solution, then we proceed. Okay, the next topic is the numerical integrations. Again, the theory is behind the numerical integration is pretty similar like the theory behind the root findings. Like you have done in the +2, you have seen that you have done the integration. Two types of integration you have done. One is called the definite, another is the indefinite. Indefinite integral means that there is no limit, right? So the idea of indefinite integral, if you look at the old SL Loney's or those old authors' book, especially from the Britain and all, they have used the word actually antiderivative. So integration is something which is against the derivative, right? Derivative means differentiation, isn't it? And integration, they are the opposite word. So they are the indefinite integrals. But then Riemann has given the idea of the definite integral. Their limits are there, a to b f of x dx, right? You have to evaluate it. Then a lot of theory has been developed. So once the definite integral came in picture, Riemann has given clear picture about the definite integrals, and this is the revolutionary one. So a lot of formulas has been used from the indefinite integral to calculate the definite integrals, right? And then area under the curves, which are the theory. But there are a lot of functions which we cannot get the formula for integrations. So one example, hot example, you know that if you have an integral of e raised to power minus x squared dx, okay, under certain limits, let us say a to b, how to find out, isn't it? So it's an error function. So how to find out, right? So how to do it? Then again, come back to the applied science. So what they have said that you look at e raised to power minus x square, it is area under the curve, right? Area under the curve. So they said that the curve which is there, you can approximate the curve by using a line. It's kind of again interpolating. So you see that the previous information which we have studied, interpolation and other things. So you see that you can take 2 points and you can make interpolating polynomial, which is line, which is approximating the given curve. You will get the rather than using e raised to power minus x square, you will get a linear curve. Use it, get the value of the integration. It is called the trapezoidal. So e raised to power minus x square, take the 3 data points there, okay, because a to b is there already. So divide in the 3 subintervals, 3 data point, no, 2 subintervals. You will get the 3 data points and you fit a curve. It is called the quadratic curves, right? Parabola curve. Okay, so rather than using e raised to power minus x square, you use that curve and solve that integral, because once polynomial is there, you can integrate it. Okay, you will get some value and it is called the Simpsons, isn't it? So like that, it has been, right? It's interesting, but it's all connected actually. So from me, actually, numerical integration is you will understand when the previous theory of the interpolations, root finding. If these things are concepts are clear, you see that numerical integration is just kind of a new recipe. Okay. And if you look at the mathematical point of view, then again numerical integration is divided into two parts. I think one is this like a trapezoidal, Simpson's rule, all those things. Another one is the new. Okay, two parts. One is called Newton-Cotes integration. Another one is the Gaussian quadrature. So they are the two major category. Okay, Newton-Cotes, it's so old one. When Gaussian things came in picture, then totally scenario changed. Two types of the numerical integrations are there. Newton-Cotes and Gaussian. They are known as the Newton-Cotes quadrature formulas and Gaussian quadrature formulas. Newton-Cotes quadrature formulas, the old one, classical ones, but they are not highly accurate. So comes like a trapezoidal rules, Simpson's rules, so on. While Gaussian quadratures actually comes through the like Gaussian Gaussian integrations, okay, by using the Lagrange polynomials, Legendre polynomials. Okay, so what is the Newton-Cotes? Newton-Cotes or trapezoidal Simpsons, basically they are the integration formulas where you can find the nodes. Actually, you can make your nodes, equidistance nodes, and those nodes will help you to find out the function value, and then you use the interpolating polynomial. But Gaussian comes from something different idea. He said that even you can make a trick to find out the best node for that. It's not that you will get the fixed node and then you interpolate it. They're telling that you can find out these nodes also through some other techniques, isn't it? So it's interesting. We are not able to cover that part, Gaussian quadrature. So here we will do only the this Newton-Cotes. So we will. Here I have written only trapezoidal and Simpsons. So trapezoidal rule is simple actually. Rather than finding the area under the curves, we are finding the area of the trapezium. That's it. Okay. Why you are finding the trapezium? Because suppose you have a curve like this. You have a curve like this, right? And you want to, that integral is this a to b fx dx. So this is the. So rather than finding whole curve, what is idea here? You can make this as a trapezium. Find out the area of the trapezium. Okay, so this is called the trapezoidal method. Of course, again, this is again a common sense. You can make one trapezium, you can make multiple trapezium. Okay, so you can call that as a trapezoidal or a composite formula and so on. You can call that. So this will be the error. And this is the numerical error analysis. How to reduce it? Okay, you can use your common sense. Okay, and that is nothing but the composite. And this is available inbuilt in the Matlab by using the routine of trap chat. So by that you can find it out. And then Simpson's rule and general integrations in Matlab. So this is the Simpsons. This is again how it has been come. I told you already. The derivation comes from the interpolating polynomial quadratic forms. Three coefficients you can find out 1, 4, and 1. Okay, through that you will get about Simpson. This is basically Simpson's 1/3 rule, and it is inbuilt again in the Matlab. Okay, by using the concept of using the routine name integral. Okay, through that you can find it out. Okay, even Gaussian quadrature is there in the inbuilt formula. Inbuilt routine is there in the Matlab. Okay, you have to see that. Because there are various Gaussian quadratures are there. Which one you want to use? You have to go through the help. Okay, when you find that's okay. That's it from my side. Any question?
Participant, if you have any question, you can write in the chat box. Participants, if you have any question, you can write in the chat box.
Okay, theory of integration completed by Jitan Kumar sir. It is very good. That's fine. So here Matlab already inbuilt routines are there. You can make use of that. If already you know it, it's very nice. Surya Rao is writing, predicting, estimating value in between two values. Yes, that is maybe for the.
So if anyone is trying to write in the chat box, they can raise the hand on this WebEx platform so that we can wait for some time because it takes time in writing the question on the chat box. So it seems there is no question. Professor Avasti, on the behalf of the organizing committee and on my personal behalf, I thank you for this very wonderful and very informative lecture. You have covered all the aspects of the Matlab as well as the later part you have covered about the numerical integration and other techniques also. And your lecture was you presented it in a very nice and very impressive manner. And I'm sure that our participants will be very much benefited by your lecture. For the participants, I would like to inform that these lectures will be available on the Canvas platform. And the recording of this lecture through the YouTube channel will also be available. The link for the YouTube recording will be available on the Canvas platform. So daily at the end of the session, end of the second session in the evening, we are uploading all these materials on the Canvas platform so that all the participants and all the panelists they can see and whenever they want to use it, they can use it also. So, Professor Avasti, I would like to make a request to you. Today, whenever you get time, you may please send me the PDF file of your PPTs so that we can upload these PPTs on the Canvas platform. And it is put in a manner that suppose some participants they have some other work or somehow they have missed the lecture, maybe due to the internet connectivity or there may be many other reasons also. So later on they can go through the lecture through the PPTs available on the Canvas platform. And then at the last of this activity, on the last day when we will be taking the quizzes from the participants, because quizzes is a compulsory part of this activity. Those who will be able to solve to obtain good marks in the quizzes, it will be like a multiple choice questions, 20 questions for 1 hour. They will be basically be eligible to get the certificate of the participation or attending the activity. So it will be nice, Professor Avasti, if you can send me the PPT, PDF file of your PPT by the end of by the end of today. And now participants again we will be coming back to this online platform at 4 p.m. where we have two other lectures, one by Professor Shruti Dubey and one more faculty would be there to talk to discuss about the numerical integration and numerical methods with you. So somebody is writing something, Satyendra Prasad is writing certificate of completion. Certificate of completion means there is no certificate of participation. Whenever you will complete the online FDP, if you are able to complete the quizzes also, you will get a certificate that you have attended successfully the FDP. Okay, it's a one certificate. You may call it as a certificate of participation or certificate of the completion. There is no distinction between these two words here. Okay. So, don't worry, it will not be very difficult quiz. The quiz will be very simple objective type question, which I am sure that if you have attended the lecture, you can easily solve the questions. It's not to worry about much, not to worry much about that quizzes, all the participants. Okay. So, thank you, let us again thanks Professor Avasti. Thank you, sir. It was great to have you here at our online activity. Yeah, so now I can close this session. Thank you.
Thank you. Yeah, please. Thank you.
मेरा ये बंद कर दो बेटा, मेरा स्पीकर माइक ऑफ, स्पीकर ऑफ था ये प्रोफेसर।